Okay, so this is going to be a longer version of the crash course for the diprotic acid lab. So for those of you who really need to kind of understand what's going on in order to really appreciate the calculations, this is going to go into more detail as to where all of this information and concepts are coming from. So the first thing to realize is that when we dissolve an acid in water, so if we have hydrochloric acid, we're dissolving molecules of HCl in water. If we have sulfuric acid, we're taking molecules of H2SO4, dissolving them in water. Not all of the molecules stay together as one. So for our strong acids, they completely separate, or what we call dissociate. And so before we dissolve it, all of the molecules are together. Each hydrogen is attached to the molecule of the acid. But once we put it in the water, the hydrogen H plus completely separates. And so what we'll see is what we call conjugate base, which is everything that's left after we remove a hydrogen, will be separate. And that's shown in yellow with the A minus on it. So those are separated by themselves. And then the H plus, that's just a proton. It's going to start attaching itself to a water molecule. So you'll see H3O plus. This is the hydronium ion. And that is this red circle with 3 light blue circles around it. The light blue circles are the hydrogen atoms. So this happens when we have a strong acid. And so what that means is that when we have a jar that has a label with a certain concentration, so remember the square brackets are the concentration, that's really the same thing as the concentration of the hydronium ions. This is not an equilibrium situation. But it does apply to the acid-base titration. So we're going to keep working with this for just a minute. Remember that there are only a handful of strong acids, and the best thing to do is just memorize what these are, and everything else is going to be a weak acid. So the ones that we often use in lab are HCl, hydrochloric acid, and then nitric acid, HNO3, and sulfuric acid, H2SO4. So if I have a 6 molar HCl hydrochloric acid sample, that has a concentration of the hydronium ions of 6 molar. If I have a 0.0012 molar nitric acid, that solution has 0.0012 molar in the hydronium ion. So why are we focused on this hydronium? Because the way we measure acids is, or how acidic something is by the pH. The pH stands for power of hydrogen. And so what we're really looking at here is to what extent, what exponential power our scientific notation goes to. So a log really focuses on what that exponential power is. And we'll see examples of this in just a minute. But the pH, the formula for it is negative log of the hydronium concentration. So in the case of the 6 molar sample, we would plug in 6 here. In the case of the 0.0012 molar, we would plug in 0.0012 here. So let's say I had a 0.001 molar sample of HCl. Now, keep in mind, this is the same thing as saying 10 to the minus 3. Okay, so the exponent on the 10 there is -3. But if I plug this into the formula, I could either plug it in as 10 to the minus 3 or plug it in as 0.001. Either way works. I'm going to find that negative log of 0.001 is 3. So this number for the log is going to be very close to that exponent. It's not always going to be a whole number, but the whole number should be pretty close to the exponent on that 10. Now, this is a 3. What if I have a lower number, a 1 or a 2? Is that a low concentration or high concentration? Well, the lower the pH, the smaller the power on the 10 for our scientific notation. And so if we compare 10 to the minus 5 to 10 to the minus 2, 10 to the minus 2 is actually a bigger number. So lower pHs actually mean higher concentrations of acids. Okay, so more acidic, lower number for the pH. All right, so now let's get into a more complicated example. When I have a weak acid, which is most acids, and I dissolve it in water, most of the molecules are going to stay together with the hydrogen still attached to the molecule. So in our picture to the right-hand side, these green blobs here are the ones where the HA molecules, acid molecules, are entirely together. And only a very small number, less than 1%, are going to split up the H plus and the A minus. Now remember that the H plus is going to attach itself to a water, and so that's going to be the H3O plus, hydronium ion. So in this case, we have most of these are not dissociated and only a very small number are dissociated. And this is an equilibrium, as you can see by the arrows between the reactants and the products here. And so we can use our processing of equilibrium to address these kinds of problems. We're not going to use equilibrium concepts for the diprotic acid lab, so we won't have to be solving ICE tables or anything for the diprotic acid lab, but this is an equilibrium reaction. So as an example, let's say I have hydrofluoric acid. This is a weak acid. The equilibrium reaction would be between the hydrofluoric acid and water molecules, and this is going to form hydronium and F minus. F minus is the conjugate base of the acid, and this has a Ka, so remember K is the equilibrium constant, of 3.5 times 10 to the minus 4. So if we start with a 2.5 molar solution of HF, and we want to know what the concentration of the hydronium ion is, we would use an ICE table. Okay, so I is the initial concentration, so we plug in the 2.5 for the HF. Water is a liquid, so we leave it out. And then the initial concentrations for the hydronium and the fluoride are just set to 0. Now, for the hydronium, this isn't 100% true, but it's close enough for what we're going to do. Then we put in the change. So our reactants are going to get smaller. So we have minus X, and our products are going to get larger, and we'll have plus X for each of those. And our coefficients are all 1s. So we have 1s for the coefficients on the X. The equilibrium is just adding those lines together. So we have each of these expressions here for what the equilibrium concentrations are. And we can put that into the formula for the equilibrium constant. So remember, the equilibrium constant is going to be equal to the products divided by the reactants, leaving out the liquid water. And then we can just plug in X for the hydronium, X for the F minus, and 2.5 minus X for the HF. So that's what it looks like on the right here. On the left, we've just plugged in the value of Ka as was given in the problem. Right? So we want to solve this. Now, we could solve this by distributing our numbers across the numbers in the parentheses here. We usually make the assumption, though, that this X is just so small compared to the 2.5 that it's not going to make much of a difference. So we're going to assume X is really small, and then we're just going to multiply 2.5 times our Ka, so that's going to give us 8.75 times 10 to the minus 4. And we're going to have that be equal to X squared. And we'll take the square root, and X is equal to 0.0296. Now, it's always a good idea when we make an assumption to check our assumption. So compared to the original 2.5 molar, what is the 0.03 basically small? Well, since we didn't have a digit after the 5, we wouldn't have been subtracting off anything anyway. So that is a pretty fair assumption. Okay, so that X was equal to the hydronium concentration, and then we could use that to find the pH. Okay, now these labs are focusing on titration. So we could figure out for adding each of our acids and bases what the pH is. But let's think about titrations we've done in the past. We have added a strong base, the sodium hydroxide, to different acids. So last fall we had a strong acid, HCl, and sodium hydroxide. And that gave us the double displacement reaction products of water and a salt. Okay. And then this spring, we titrated vinegar with sodium hydroxide. Vinegar is acetic acid, so that's what this is here. Now I've moved the H out front so it parallels the other acids, but sometimes you'll see it at the end. So acetic acid plus sodium hydroxide is going to give us, again, water, and then the salt, which is sodium with the acetate ion. So those are examples of things we've titrated. Now, when we titrate, especially when we are using a weak acid, it's kind of like the disturbance to an equilibrium that we talked about with Le Chatelier. So in last week's lab, we had a system at equilibrium and we either added something or we took away something. Maybe we added heat or removed heat. So in this case, when we add the hydroxide is going to react with any of the H3O plus that's around and remove it from the system. So remember, our original equilibrium reaction looks like this: HF plus H2O in equilibrium with H3O plus and the conjugate base F minus. And when we add the base, the sodium hydroxide, to the flask underneath the burette, that hydronium is going to react with the OH, forming neutral water. So we pull the H3O plus out of the solution. That means the pH is going to rise. It's going to be less acidic, so the pH is going to start going up. And because this is an equilibrium reaction, we're also going to shift the reaction forward or to the right, which means we're going to start using up some of that HF. So we're going to keep doing this until we have used up all of the HF. And when we have used up all of the HF, this is what we call our equivalence point. And this is an important point because at this point, the moles of OH from our burette are equal to the moles of HF that were in our original solution. And then we can use that number of moles to determine either the concentration, as we did in previous titrations, or the molar mass, which is what we're going to be doing in this lab. So once we get to the equivalence point, the OH isn't going to be reacting with HF anymore because there isn't any more HF. It's all been used up. And it's going to start reacting with H2O, and we get a side reaction, and we've got other stuff going on. Okay, so then the question becomes, how do we know when we've hit this equivalence point? And this is where a titration curve can be really useful. Okay, so a titration curve is plotted where pH is on the y-axis, the vertical axis, and the volume of your titrant, so usually sodium hydroxide, is on the bottom and on the x-axis. And I've color-coded this a little bit to kind of indicate that below 7, our pH is acidic, and above 7, our pH is basic. So the red corresponds to like red litmus paper litmus paper will turn red if it's acidic. Litmus paper will turn blue if it is basic. Okay, so usually when you have a complete titration curve, you're going to be in both of these areas, but you often spend a lot of time just in one of these areas. So either just in the acid range or just in the base range. All right, so let's look specifically at a titration. When you start your titration curve using graphical analysis, you're going to get just a couple of data points and it's going to auto scale, which means it's going to try and spread out the data points as much as possible. And it's going to look more like what we have on the left here. So notice that we have the pH being measured on the y-axis and the milliliters of hydroxide on the bottom. But we have kind of a line that is tilted upwards here. Now, when we look at this in the grand scheme of things, when we look at the overall titration, it's not going to seem like this is tilted up very much at all. It's going to look pretty flat. And that's because the scale of our vertical axis is going to change quite a bit. So normally we're going to look at this on a scale of 0 to 14. And you'll be able to adjust your graphical analysis so that it will do that. It will show the 0 to 14, but it does have a tendency to switch back to auto scale. So you may end up seeing more the version that's on the left. So the difference between these is that we don't have quite as much of an upward tilt here. It's the same data. There still is a slight upward tilt of our line, but it doesn't look quite as slanted upward. It looks flatter. And that's because we've got a larger scale in the vertical direction. So at first, and notice this is 20 milliliters here that have been added. At first, the pH isn't going to be changing a whole lot. Now for your titration, it very well may be less than 20 milliliters. So definitely follow the directions in the lab. Now, as you get close to the equivalence point, notice the change in the shape of the curve. Instead of being flat, it's going to start to curve upward. And this is an indication that you need to slow down, by which we mean add smaller and smaller amounts of your base. So our first few data points are 5 milliliters apart. And then our last few data points are only 1 milliliter apart. We're going to make them even smaller than that, just adding a few drops at a time. Okay, so this is going right up to our equivalence point. And notice that the farther along we get in here, the more vertical this graph gets, the more the right-hand side and the left-hand side look a lot alike. Okay, so here our data points are nearly vertical. That is the region where we've reached our endpoint. Now, typically, when you are using an indicator like phenolphthalein, you're looking for a color change. Well, why does the color change so rapidly? Because just adding a couple more drops is going to change this pH in the vertical direction quite a bit. So from this point, adding 2 or 3 drops could make it go from a pH just above 6 to a pH around 9. Okay, that's a big change. And phenolphthalein changes color around pH of 8. So we'll get that color change there. But our volume change is going to be next to nothing. It's going to be hundreds of milliliters. Okay, so we won't have much of a change in the volume, but we do have a change in the pH. So a titration curve is another way to look at this where we don't have to have an indicator that changes color because we can just find where on the graph this is very vertical. Now you're going to go a little bit beyond the equivalence point. And so your graph is going to end up looking like this. It's going to look kind of like an S. And so you'll have a region where this is mostly vertical. Remember, we said that's our equivalence point. And you're going to find the data points that are surrounding this vertical region. So you have to kind of pay attention to, okay, what volume is this near? And then see where the pH change is the largest in this region. Those 2 data points you're going to average together to find the volume. So like take that vertical line down. The volume here at the equivalence point is something we're very much interested in, because this is how we're going to figure out how many moles of hydroxide we have. So we're going to take that volume at the equivalence point and take the concentration on the label for the bottle for the sodium hydroxide, or maybe it's written on the board, in order to determine what the number of moles of hydroxide are. Okay, so remember that this volume is directly below the vertical change in the equivalence point. All right, so at the equivalence point, the moles of hydroxide is equal to the moles of the acid. Now remember, this is moles, not concentration. Okay, so we have to find the moles by multiplying the molarity of the sodium hydroxide times the volume of the sodium hydroxide. So if I look at this graph, this volume is about 37 milliliters. So I change that to liters, 0.0375, and I multiply that by the concentration. So this is assuming we have a concentration of 0.0988 moles per liter. And that would give me 0.00370 moles of hydroxide. And the reason I want to know how many moles of hydroxide is that is equivalent to the moles of the acid, the HF in this case. Now, this is the moles of HSF from the initial concentration, from what was first put into that bottle or first put into the flask or the beaker that we were doing our titration with. How many moles of the acid were in there? Now, from there, we can do a couple of things. We could try and find the concentration of HF. So remember, the square brackets are the concentration, in which case we take those moles that we just found and divide by the initial volume of the acid. So this isn't going to be the 37 milliliters. This would be whatever we pipetted in. So if we were doing our vinegar lab, we pipetted in 5 milliliters. This is what we would divide by. In today's lab, we're not using a liquid, we're using a solid. So we're not going to pipette it in, and we're not going to try and find the concentration. Instead, we're going to have a mass. And we're going to use that mass to find the molar weight. So think about molar weight. What are the units for molar weight? That's grams per mole. So we're going to take the grams that we weighed out, the mass, and divide it by the moles of the HF. And that will give us the molar mass of the acid that we're working with. All right, so titration curves also have other parts to them that may seem pretty uninteresting, but they can help us with information too. So leading up to our equivalence point, we have this flat area. The flat area is what we call the buffering region. And it's a buffer because even though we're adding a base, or if we added an acid, we're not changing the pH a whole lot. It's staying right around 3, 3.5 in this region. Okay, so that's a buffer because it buffers the pH from changing a whole lot. We can figure out what the kind of average pH of this region is by looking at the half equivalence point. So what we do is we take the volume at the equivalence point and cut that volume in half. So here we had 37. I cut that in half, I can have 18.5. And if I look at the pH in that region, that's going to be the rough pH of the buffering region. But I can also find something else that's important too, and that's called the pKa. So I take where that volume is, the half of the equivalence volume, go up to where my curve is. And you might need to draw a line connecting these dots here so you can see where it is, but I take my line up to the curve and then go over to the side, figure out what the pH is, make sure that it's nice and horizontal, that it's not coming in at an angle. That pH is equal to what we call the pKa. Okay, so that's what you're looking for in this lab. All right, so you can find both the molecular weight and the pKa. So from the graph, The pKa is found by looking at the pH at half the volume of the equivalence point. That's what the pKa is. pKa is also equal to the negative log of the Ka. So just like we found pH by negative log of hydronium, the pKa is negative log of the Ka. And what is the Ka? That's the equilibrium constant. So for this reaction, way back at the beginning when we started talking about HF being in equilibrium, we said that Ka for this reaction was 3.5 times 10 to the minus 4. Okay, so if we take the negative log of 3.5 times 10 to the minus 4, we get 3.46, or about 3.5. So let's go back and look at where that happened on the graph. Our tie lines here, our tie lines here go from the half equivalence point up to where it meets the curve and over to the side where the pH is. This is right about at 3.5. Okay, so we can find it graphically, or if we happen to know what the Ka is, we can find it using the negative log. All right, so let's talk about diprotic acids. A diprotic acid has more than one ionizable hydrogen. So sometimes molecules have hydrogens that are just so strongly covalently bonded, they're not going anywhere. But if they're attached to an electronegative atom, say an oxygen, for example, or a halogen, then they are ionizable. They can come off as an H+. So if there's more than one of those, we call it a polyprotic acid. If there's two, that's specifically a diprotic acid. Now, when we have the hydrogens coming off of these, they're each going to come off in turn. Instead of all of the hydrogens on a diprotic acid coming off at once, they'll come off one at a time. So let's look at the right-hand side here. Here's some examples of some diprotic acids. And I want to focus right now just on the H2SO3. This is sulfurous acid. So when this dissolves, initially it's going to start losing one of these hydrogens with the other one remaining behind. And it won't be until every molecule has lost that very first hydrogen before the second hydrogen starts coming off. Okay, and so that's going to affect what our titration curve looks like. Oops. Looking at some of these other acids, it's very common for polyprotic acids to be organic. So organic, remember, is going to have a lot of carbon. So you see carbon in here. This one, the second one is oxalic acid, and it kind of looks like a palindrome here. So we've got this COOH and its mirror image. Okay, and then the one below is malic acid, and so it has a COOH, and then it's in parentheses with a 2. So that means there's 2 of them. And then down below, I think that's maleic acid, again, the COOH with a 2. So the COOH is carboxylic acid, and a carboxylic acid is just a functional group. It's a part of a molecule, not the whole molecule. But whenever I see that group, COOH, that tells me I've got an acid. And the more of those that I have, the more of a polyprotic acid it is. Okay, so if I were to do a titration curve of one of these, instead of having just a very simple S curve, I'm going to end up with more of a double S curve, something that looks like this. So we've got the little s at the beginning, with it increasing right around 10 milliliters, and then the second one at about 20 milliliters. All right. Otherwise, it looks pretty similar. Because I have 2 places where I have this rise, I actually have 2 equivalence points. So I have the first equivalence point is going to be on the right-hand side, and the second the first equivalence point is going to be on the left-hand side, and the second equivalence point is going to be on the right-hand side. Now, usually the second equivalence point is easier to see. So you can see here it's more vertical in the second equivalence point than it is in the first equivalence point. And so often that's the one we use for our calculations. In each of these cases, we're interested in what the volume is. So we can take that equivalence point down to the x-axis, and we can see that our second equivalence point is right about 21 milliliters, just shy of 21 milliliters. Notice the first equivalence point is almost exactly half of that, just above 10 milliliters. That's really significant because that means that our stoichiometry is staying the same. With one hydrogen, I have 10 milliliters. With two hydrogens, I have 20 milliliters. Okay, so what can we do with this? At our first equivalence point, everything that we said about just a regular monoprotic normal acid applies. The moles of the hydroxide are equal to the moles of the acid. We get the moles of the hydroxide from the molarity of the hydroxide and its volume, the volume that came out of the burette. And then we can find the molar weight by taking the mass divided by the moles of the acid, which is the same thing as the mass divided by the moles of hydroxide because they're equal to one another. But like I said, sometimes the first equivalence point is hard to see. I gave you an example where it was a little easier, but sometimes it's hard to see. So if we look at the second equivalence point, the moles of hydroxide is equal to 2 times the moles of the acid. So since we got rid of both hydrogens, we had to put in twice as much hydroxide. Now we still find the moles of hydroxide from MV, from molarity times the volume, the molarity of the hydroxide times the volume from the burette. That is still the same. But when we're calculating our molar weight, and we want to do mass divided by moles of H2A or moles of the acid, we have to remember that the moles of the acid is actually half the number of moles of the hydroxide. So you have to take however many moles of hydroxide you calculated and divide it by 2. All right, so let's look at some sample calculations. Let's suppose that you weighed out 0.1058 grams of an acid. Now in your lab, you're not going to know what this acid is. So you don't have a formula to look at that you can calculate anything. From the bottle of sodium hydroxide, the molarity is 0.0988 moles per liter. And then when you did the titration, or when we did that titration, we found that the complete titration was done at 20.92 milliliters. And the first equivalent point was at 10.4 milliliters. So what are we going to do with this? Let's look at the second equivalence point first, because I said a lot of times that's clearer and easier to see. So the first thing we want to do is find out how many moles of hydroxide we used. So we're going to take molarity times the volume, the 0.0988 times the 20.92 milliliters. But remember, since molarity is in moles per liter, I'm going to multiply by the volume in liters. This is going to give me 0.00207 moles of hydroxide. I want to know how many moles of the acid I have, so I have to cut that in half. So that's going to be 0.00104 moles. Then to find my molar mass, I will take the mass, 0.1058, and divide by this number of moles, the 0.00104. And that's going to give me a molar mass of about 102. So remember that molar masses come from the atoms that make them up. So if you get a molar mass that's less than 10, that means you couldn't even have one carbon atom in there, let alone a COOH group. Okay, so you want to have molar masses that are probably in the range of 100 or above 100. You know, something like 60 is reasonable, but something like 2 is not really reasonable for this lab. Okay, so what if we decided to look at the first equivalence point? At the first equivalence point, we're still going to do molarity times volume, but this time we're going to plug in the volume of 0.0104 milliliters. And this is going to give us the number of moles of 0.00103 moles of hydroxide. And at this point, that's equal to the moles of acid. So I don't have to do further calculations there. And then I divide my mass by my number of moles, and I get 103 grams per mole. So you'll notice that the masses were very, very similar, 102 versus 103, but not exactly the same. Okay, this is experimental error that happens sometimes, but they are pretty close to one another, and they should be. Either way that you do it, you should come up with something that's pretty similar. Okay, so finally, part of the lab you may be asked to do is to find the pKa for each ionization. So the first pKa is going to be halfway between the first equivalence point and the start. So we said our first equivalence point was just above 10. So halfway is going to be about 5. And so we could draw a line up from where that is and go over to the side where the pH is, and we can determine what that is. And so here it looks like it's 2.2, but you can get a better answer by looking at what your data table says in that region. So I can say, oh, okay, where's my data point that's very close to 5? What's the pH at there? And that can give you a good answer. So the first pKa, pKa1, is not too bad. The second pKa is a little bit trickier. You'll notice that the spacing here is very regular, so kind of keep that in mind. When we go to our second equivalence point, so remember this is the one that's just above 20, I don't want half of that because half of that was my first equivalence point. I want halfway between the two equivalence points. So what I could do is I could say, what's the average of my two volumes? And that would give me something just above 15. Or I could say, what is 3/4 or 3/4 of my 21 milliliters? And either way, I should get just above 15. And again, we're going to do a tie line from the volume up to where the curve is. Notice I've drawn in where the line is because this is coming between data points. And then from where it hits that curve, I'm going to go over to the y-axis. And at the y-axis, I'm just below 6. So my pKa2 is going to be 5.8-ish. Okay. Now, remember, this is for the generic acid that I've shown here. This isn't exactly what your data is going to show on your lab. So use the numbers from your lab in order to solve the problems that are posed to you. But these are the basic ideas that will help you get through the lab. Good luck to you.